and gentlemen, welcome to the Wayne Township Education Foundation Science Claus, starring Rick Crosslin and Keith Ramsey, with special guests, presenters Edison, Justin Abner, and Mary Mason. Now to introduce the Wayne Township Education Foundation Executive Director, Lisa Bays.
Good evening, everybody. Thank you for joining us for Science Claus is Coming to Town. As Mr. Montgomery said, I'm Lisa Bays, the Executive Director of the Wayne Township Education Foundation. For those of you who don't know what we do, when a teacher has a brilliant idea, we raise money to try to create resources in the classroom for them. Everything from DNA fingerprinting equipment, we help fund Science Summer Safari. Do we have any kids or parents even who attended Science Summer Safari? Nice. So we help provide funding for that program so it doesn't cost you so much money to do it. Additionally, converting a diesel engine to biofuel here at Ben Davis. Teachers have amazing ideas every single day, and we fund about 200 of those awesome ideas every year. So thank you for joining us tonight. Our sponsors help make programs like this happen. I want to introduce several of them. Our major event sponsor for tonight include the Indianapolis Airport Authority. And then if I could have Linda Osborne stand up. She's joined us with the Indiana chapter of the American Chemical Society. So we thank them for supporting Science Claus. Additionally, I want to thank our platinum sponsors, again, the Indianapolis Airport Authority, IU Health, Canon 4, and RX Health Centers. With their support, we are really able to extend what we're able to do in our community, so we thank them as well. The Ben Davis High School Key Club is selling concessions. They will be here the whole time, so we hope you, and it's bargain pricing, a buck for anything. So we hope you go and support them tonight as well. With that, I'm so excited to introduce our scientists. Many of you know them. I first want to introduce our scientist in residence, Mr. Crosslin. Additionally, I want to introduce Mr. Keith Ramsey from Bridgeport Elementary. Mr. Justin Abner from Maplewood Elementary. Miss Mary Mason from Chapelwood behind the PowerPoint. And Mrs. Allison Kempers from Wayne Township Preschool. And with that, I turn the program over to Science Claus himself.
Thank you, Lisa. Let's give Lisa a round of applause. This is our third year doing this science show, and I'm so happy to do this at Christmas time. I had an opportunity with my family to go to London, England, and we visited the Royal Institute. Now, the Royal Institute, you're going to learn a lot about some of the scientists tonight, but the Royal Institute is still active in London, and every year they do a Christmas science show for children and for the public. And it was started in 1825. And I love science, and I love kids, and so I thought we should start doing our Christmas show. So tonight and every Christmas we do this, it is following in the footsteps of the famous Michael Faraday, who you'll hear more about later on, who has said and seen, to make a fact my own, I need to see it. A fact seen is a fact possessed. So he wants to show things. And all of us up here, we teach a lot, we read a lot, we do a lot, but when you see it, it's easier for me and hopefully for you to understand. So we're going to show you the slide a few nights tonight. There's some rules. We're probably going to break them, but for you guys, some of the rules of the show is that the first rule, there's going to be some loud noises, right? Let's hear some loud noises, some sound energy. Oh yeah. There's going to be some loud noises. If you don't like loud noises, we'll make it louder. No. If you don't like loud noises, we'll show that and you guys can cover yours, okay? Deal. Next. My motto is, this is science, try it yourself. But there's a few things you probably should not try at home. So if you see this guy, you should probably not try this at home unless your parents are helping you or we're there helping you. So if you see that activity, don't do this one at home. Next, if you see dinosaurs, run. Exits are here and here, okay? Off to the side. So if you see any dinosaurs. We have some volunteers coming. We've already passed out the volunteers. We already selected them. And they'll be coming over here and coming up on stage. So let's get started. We got a lot of things. Let's see what happens. You guys ready? Okay, our first one is going to be a loud noise. And so where's my friend? Yes, come on up. Yes. Yes. Hurry up. No, not this one. Right. We're going to do the knock your socks off first. My elves, where's my elves? Let's help. Here we go. It's my first. Here we go. Here we go. This is a 5-hour show, by the way, and mostly to get the people off on the stage. So the first thing we're going to do is called knock your socks off. You're going to learn a lot about chemistry tonight. You're going to learn a lot about physics and movement. And come on up, come on. I got your goggles, good deal. And let's get over here. Can we get, you guys help me get over here? So the first thing we're going to do is, this one is kind of scary. We needed a good victim, volunteer for this, okay? Do you have insurance? You don't know? Okay. All right, so what is this called? This is called knock your socks off, okay? You use your socks or my socks? Let's use my socks. They kind of stink, though. You want to smell that? No. No, it's not too bad. You'll get used to it. No, yeah. Hold that for a second. Okay, well, all right, let's see. Knock your socks off. All right, here. We'll put it in here like this. And we're going to do a chemical experiment. We have a solid. See this solid right here? It's a solid. And we have a gas, we hope, and we've got some liquid. So let's see if we can get this going here. Let's see, move some of these socks out of the way. And see if I can light one of these. Are you all right? Let me put my goggles on. I don't want anybody to get hurt, especially me. It's a long show. Okay, so let's see. We're ready? I hate this part. Where are you going? Let's stay closer. Okay. And nothing. Here, hold that for a second. Maybe hold that. Maybe I'm doing this wrong. Yes! You volunteered, didn't you? Okay. Let's try that one. Let's see what happens. Ready? Hold it, tip it down so they can see. Ready? Hold it close to you. Let's see. Nothing. Maybe I'm doing something wrong. So we tried a solid. We tried a liquid. What's left? A gas. Okay, hold it. Let's see if we can make a gas. Let's see. Let's put. I'm going to add some water. Now this is an old chemical that was actually used in miners' helmets. We mixed calcium carbonate with water to make a carbide. That's pretty cool. Yeah? You want to hold it? Okay. I don't blame you. Well, let's try the experiment then, all right? Let's see. I have here some calcium carbonate. Oh, it'll be all right. Let's see. I hate this part. You ready? Remember, you volunteered. Okay, let's get, so here, closer to these people. Okay, let's see. You hold that. Yes, you volunteered. Okay. Ready? Grab my arm. Are you guys ready? Who should we point him at? Anybody? Those guys right there. Okay, here we go. Grab my arm. Let's try it. 1, 2, 3. It didn't work. Why? What did we forget? What did we forget? Gas. Gas. Okay. We forgot the gas. Let's make some acetylene gas, the same kind of gas that's in acetylene torches. Torches, yeah, for welding. Very dangerous, very dangerous. Are you ready? Is she still on stage? Okay, here we go. Shut your ears, everybody. It's making a nice gas. Go and grab my arm and touch it there. That's grabbing my arm. Why are you shaking? Here we go. 3, 2, 1. Let's see what happens. guys. Have a seat while you're out here. Well, if they're all like that, the insurance company will be happy tonight. That sucks. You have a seat, thank you. Our first segment's on electricity. And so we got some cool things here, and we're going to try to do some electricity. Think about electricity. For 6,000 years, people have thought about electricity. Even the ancient Greeks thought about thunder, lightning, thunder. And they would find a piece of amber and rub it to give off a shock. So we're going to work on static electricity. The ancient word for amber is the electron, and that's where electrons come. The static electricity we're going to talk about today is everywhere. Without electricity, your car wouldn't work. Your house, your phone, your computer, airplanes, electricity is everywhere. In fact, a horse can't walk without electricity contracting its muscles. I can't talk or move without electricity. Our brains, we can't even think without electricity. In fact, electricity is one of the 3 of the 4 forces in the universe. 3 of them have to do with electricity. So our first one is static electricity. You guys want to help me with this one? So the world is filled with charges. This one you can try at home. This we got from a golf club, and this is some furs, and we're now charging it up because there's negative and positive charges. And if you do this right, it should be attracted to it, and then it should be repelled by it. Ooh. Now that's got to be a lot better. Ooh, ready? Okay, that's better. And so this mylar wants to get away because it's attracted. If I touch it, now the charges are starting to discharge and get away. So this is kind of fun. You can try this at home, just rub it. You may have seen this when you get into cold sheets at night, or go home tonight, turn off the lights in the bathroom, and comb your hair. You'll see and hear little blue sparks of static electricity. So we're going to try something here. We have a different one. There was a guy by the name of Robert. Let's look at Robert Van de Graaff here. Robert Van de Graaff, he was a guy that was at MIT, and he invented the Van de Graaff generator. So we have some generators. Our Van de Graaff people, come on up. So this is a big wheel. It's kind of dangerous, so I hate this part. 200,000 volts will come through here. If I turn this on right, let's see what happens. This big wheel is starting to charge that up. The negative charges want to get away. I hate this part. Aren't you guys doing the same thing I'm doing? Do I have to be the one get electrocuted? Oh, here we go, ready? Oh! So right now, all those 200,000 volts are going through me. Let's turn it up just a little bit. But there's no current. It's the current that will hurt you. Just like the current in a river, which shows you direction and how fast it's going, there's very little current. So it's going through me, and even if I step off, I should be able to survive this. Back up just a little bit, sweetheart, because you might be part of the experiment. I am being grounded. Now listen, maybe you can hear. All that volt is going into the ground. A lot of people would put up a lightning rod in your house, and by doing that, I just caught some more electricity going through the floor. That'd be some metal there, and that will take the electricity out of the sky into the ground. Let me take my hand off of this. And we turn the lights off, Mr. Montgomery. Let's see what happens here. Watch carefully. You might see a And even if I turn this off, this is why when you go outside on a day when there's a thunderstorm, even when you don't see or hear thunder or see lightning, the clouds are still charged. You don't want to be the tall person, doity, walking by, because you will become part of the discharge. Most lightning strikes are from cloud to cloud or from cloud to ground, and rarely sometimes from the ground up. So you want to pay attention when it's time for that. We have some volunteers. Let's turn the lights back on. And come on over here. Thanks for coming up. What school do you go to? McClellan. Okay. Step on up there, and you probably won't get hurt much, okay? If you follow directions, all right? Okay, put your hand on there. Okay, got your hand on there. Now, you notice why we selected her. Hopefully we can get all those thousands of volts to go through you. You over there? Mary, you ready? Justin, who's that?
My wife.
Your wife? How's things going at home? Perfect. Maybe not after this. All right, we're going to turn it on. Are you ready? As long as you keep your hand on there, you should be okay. Shake your head a little bit like that. Take your head, go like this. Wow, shake it one more time. How are we doing over there? Now, this is the new hairdo. We call it the Van de Graaff hairdo. Shake your head a little bit more. That's pretty good. She is now charged up with several 100,000 volts. And we need one more volunteer. The young man, come on up here. Yes. Come on this way. Quickly. It's really charging up. And I'm going to turn this off. How are we doing over there? Go over here. And keep your hand over there. Go around the front here. All right. I tell you what. Take your hand off now. Take your hand off there. Point your finger and touch him on the nose. Good job. Good job. You did good on that. Have a seat. Sit down, please. You should give it once. Come on, get up here. Let's see here. And I want you to hold that with that hand. Put your hand on it. We discharge it. Now you'll be fine. Go ahead and put your hand on here. So this is both conductors and insulators. The conductor, which allows electricity to go through it, is the aluminum. The glass is the insulator. Are you ready? Let's see. When I hold that hand out to your left there. There we go. Let's see if we get him charged up. And he's shaking. You're now charged up. Stacy, you getting anything down there? Okay. All right. And let's turn that off. And I hate this part. Go ahead. Touch my nose. I hate this part. Oh, let's give him a round of applause. Thank you. So we can try one more of this. We can charge this up, and we get this balloon, and it comes to it. When I discharge, it goes to it. When I let go, it goes away. When I discharge, it comes to it. Go away. Yeah. It goes away. Would you guys come down here? Justin and Stacy, come on down here. Let's try this one. Both of you guys come down here. This is an experiment that was done in the parlors in the 1700s. A scientist, Justin, you're over here. Stacy, come on up in here. And this was a big deal back in those days. Put your hand on here, Stacy. And we're going to charge Stacy up. We hope. All right, shake your head a little bit. Justin, this will work better if we give her cut her hair. Would you get the scissors? No. Okay, so we're charging her up. Now in the 1700s, this is what they would do. This was called, you can take your hand off, don't step down, the electric kiss. How's that marriage set? Just give her a round of applause. Thank you. The next slide, what we got? Okay, so you can read about in your program, you can read about some of these guys. This one's Stephen Gray. He invented conducting and insulating. He would have a boy dangle, hook one of these, some of it up to him, and he could have feathers and gold leaf come up to him. Let's take a look at the next one here. We got, this is one of my favorite, Michael Faraday. Can the Faraday kids come on up? We got some Faraday kids here. So Michael Faraday, with the Faraday volunteers, come on up, please. You three, yes? So Michael Faraday discovered that if you had a magnet and you moved wires inside of it, you could transfer this kind of energy into electro energy. In fact, he found the word electromagnetic. He went on to find the word electrochemical. So let's see what happens here. That's pretty cool. Now, when he made this, the light bulb had not been perfected yet. And so when he made this, he famously said, I don't know what we'll use this electromagnetic force for in the future, but I do know the government will tax it. So let's see, we got some friends here. Okay, this is kind of fun. My young man, come over here. Come over here first here. Let's see, we're going to make a human circuit. Put that down. I didn't remember your dad volunteered you. Remember that, right? Okay, put your finger right here. It's better if you lick your finger. Go ahead, lick your finger. Go on, lick it. There you go. Okay, put it right there. Because the salt in your saliva is a good conductor. You ready? 1, 2. What happened? Wait. No. Keith, where's the tape? We got a tape. No. Oh, wait a minute. This is not working. What do we have to do? Lick. I'm not going to lick his other finger. Lick your other finger. And now let's close the circuit. Now, I'm going to have electromagnetic energy transfer, hopefully to sound and movement. Are you ready? On 3, okay? On 3. Ready? 1. What? You didn't say anything. We're going to do it again. In science, we always do it twice. One more time. All right. We have some volunteers. Thanks. Give them a round of applause. That's right. Let's hold hands. Put your hands in here. So this experiment was done in France, in the capital, for the King of France in the 1600s. He had 100 soldiers line up and hold hands. And to the amusement of the king, faster than the speed of sound, electricity went through. Ready? I can't believe you're the first one. Ready? Hold it here. What? It's not working. What do we have to do? We have to close the circuit. Here we go. Here we go. You guys doing good? Are you nervous? Because you can sweat. That's really good. That salt in your sweat is even better. On 3. Ready? 1. What are you doing? Look at them, not me. 1, 2, 3. Let's give a round of applause. Thank you. Michael Faraday, the dynamo. This is spinning, making electricity going this way. It took many more years for Tesla to find a way to make electricity go back into a motor and a generator. And I introduce Keith here with Tesla.
So in 1807, Humphrey Davy, an English chemist, realized that we needed more light than candlelight or oil light. And so he found a 2,000 cell battery could jump plasma from one stick of charcoal to another. And if that spark gap was just the right distance, it would create a bright light. And so guess what I did? I swiped my son's car battery for this experiment. And I think he's here right now. And I got a couple jumper cables. Now, if you have those paper glasses that we gave you as you came in, go ahead and put those on, because we want to protect your retina. If you look directly at this, it can burn your retina. Now, some of you adults out there, if you feel like you've already seen too much in this light, go ahead and look directly at the light.
Keith, I don't think these protect us from the retina. So let's use this shield.
Oh, Rick wants to use the shield.
Yeah.
All right.
So as he said, arc light. Arc light they also use for arc welding. And at Ben Davis, they teach welding. And this is one of their brand new welding shields. And we'll see if we can get this. Let's bring the house lights down. And let's see what happens here. Now you can probably see that coming through. And brighter and brighter. And you can see the shadows up here from this. And this is really bright. I'm not going to look at it. Otherwise the show will be a lot quicker. And when was this, Keith?
1807.
And so the streets of Paris were lit by this. Now you might think, how could you have a light like this at night? The thing on the right here is called a moon tower. If you notice, it's down in the basement. They would burn that. It would shine straight up on a big mirror, and people could walk the streets at night. That's pretty cool. Keith, I think you have something else to surprise us, don't you?
Yeah, I do. And this is an
Lights back on, please.
arc light. And what's interesting about this is that after his invention, people realized that this could be used in industry, in the medical field, and of course in movie theaters where you need a lot of light. And so this is a 150-year-old arc light. And it's special because instead of just having 2 sticks like this one does, it has 4 inside of it. You can open it up. And you can see those here. And just like in our experiment here, you're going to jump a little bit of plasma between those 2 sticks as energy passes through it. One of the things I really like about this old arc light is that it actually has a little chimney on top. So the smoke actually comes out of the top while it's on. And check our plugins over there. Sure, it's good.
This was used in theaters and movies, even during the daytime when before film could be as rich as it was. They would have these and shine them on the actors during the day to really get the light coming on them. How's it going, Keith?
We're working on it.
Keith, you got like 30 seconds and I'm going to shock you.
I know, keep going, keep going.
I'll tell you what, you keep working on that?
I'll keep working, you
All right.
keep going.
So that jumps us ahead to this guy right here, Thomas Edison. And if you take a look at Thomas Edison, it's hard for me to explain Thomas Edison to you because he was such a hero. The whole United States, including Europe, if Thomas Edison said it, they believed it. He first worked on improving the telegraph. Then he got interested in the light bulb. In fact, he didn't invent the light bulb, but what Thomas Edison did was he improved the light bulb. In fact, if you ever screw in a light bulb, that was because of him. And a famous quote of Thomas Edison is that he spent over 1,000 different experiments trying to find the filament. That's the little part right in the middle. In fact, in his lab, they tried so many things to burn that would stay lit, that a light bulb would only stay lit maybe 10 seconds, and it would burn out. They tried everything. They had a guy from Sweden that tried his mustache hairs. And of course, the worker from Germany thought maybe German hair are better. They didn't. 10 seconds. But one day, he made a light, and they turned it on, and that light, when he turned it on, lasted for 10 seconds, 15 seconds, 1 minute. After a minute, his workers were going crazy. It's lasting a minute. After an hour, they were jumping up and down. At 2 hours, they were pulling out each other's hair because they could not believe that they got that light to work. It was a piece of thread that was carbonized inside of a vacuum tube. After 10 hours, they all sat down on their bench and watched this light burn because they knew that they had brought the light of day into the dark of night. They knew now that people could go shopping, that people could walk down the street, that people could stay up and read and go to school. Because before that, you guys want to light those 2 lamps right there? Before that, people had to use lights like this, hurricane lamps we call them today. Go ahead, light that one up there. But Thomas Edison was able to bring this light into the world. How are we doing, Keith, on that one?
Still working on it. It's temperamental. It's 150 years old, so sometimes it takes a while. Got a spark.
Turn it down a little bit, Justin. And you see the problem with having light in your house, every house that people had money would have gas that came from coal. They would liquefy coal, make it into gas, and into their house, and you could see the smoke coming, and the smoke, turn that down the other way there. Thank you. And this is how they would light their houses. Once Thomas Edison came up with the light, a flip of a switch. But there's a problem with this. Let's check this out. You guys ready for this? This one's kind of interesting. You ready? I'm going to plug this in, and this has to be quick. If you notice, Mary, you want to do this, and Justin, you want to do this too? We're going to plug this in, and I've broken the glass. Here's what happens when the filament touches air. Ready? You have to watch this quick. It oxidizes. Ready? 1, 2, 3. So a light bulb would only last short amount of time before it would burn out. So the modern light bulbs are put in a vacuum without air. So the real enemy of this is not the vacuum, but it's oxygen. So we're going to try this right here. Here's some liquid nitrogen. Maybe we can maybe we can get this to work. Here's a broken one with some liquid nitrogen. That's 327 degrees below zero. That is pretty cold. As a matter of fact, I have to be careful with this. It's boiling right now because that glass is pretty hot compared to 327. Can we turn the lights down, Mr. Montgomery? I'm going to put this in here. It should start to boil. And you guys over there, how are we doing over there? Good. Ready? I'm going to turn my light on and see what happens. That's pretty cool. It's a broken light, and the filament cannot get to oxygen because it's completely engulfed by liquid nitrogen. This is supposed to clap. This is really how cool it is. Oh, yeah. Pretty amazing. How we doing over there, Maplewood? So what's going to happen when I pull this right out? It should oxidize. I love that you use that word. And it should last about a second. Let's see what happens. 3, 2, 1. And it's gone. And that was pretty cool. Thank you. What's next, Aaron? What do we got here? So that's a little, I think we're going to do one more thing with our, this was Edison and his world. He got things going really good. But this, it's hard to find a filament. Keith, don't you have a better filament we could try?
Yeah, you don't need a light bulb, Rick. All you need is a pickle.
Wait a minute, pickle?
A pickle! Who needs filament when you can just use a pickle as your light bulb? If you have a pickle soaking in salt water long enough, a cucumber, it becomes pickle. And everyone knows that sodium chloride is charged. Sodium is like the anode of a battery. It has a positive charge. And the other side of it, chloride, is like the cathode of a battery. It has a negative charge. So if you simply put 2 screws in each end of a pickle, you are attracting electricity from sodium to potassium right through the middle of your pickle. And so that's what we're going to do. And we're going to see what happens when electricity passes through a pickle. All right, you have your pickle?
Ready.
Ready to go? Okay. So what do you think is going to happen? You think the pickle will glow? What do you think is making it glow? That electricity, yeah, electrons are traveling negative to positive. In 3, 2, 1, pickle power. Give it a second.
I'm sticking with Edison.
Look at that pickle. Look at that pickle over here. Pickle power, people. You see it? Tell them it's nice to eat your heart out. We've got pickle power.
Do not try this at home, please. Okay, ready? So, Keith, we'll take care of the pickle. I think your next up is...
Yeah, you know, this pickle light in wireless transmission of electricity reminds me of Nikola Tesla, who in the 1800s, his dream was to transfer electricity wirelessly. He dreamed that every house would have a Tesla coil in the basement, and this Tesla coil would turn on all the electronic devices in your house without any electric wires in your walls, without any outlets. And so, of course, we have this invention here. This is a Tesla coil, and it works with 2 primary coils, which reminds me of Michael Faraday's experiment with induction. So if you have a copper wire that's wound in a coil, and you have a magnet that passes through the coil, that induces a volt of electricity. So what Tesla did is he built on Faraday's genius, and he used 2 coils. There's a primary coil at the base,
And that primary coil has its own capacitor. And that capacitor absorbs most of the energy. And then there's a spark gap to a secondary coil. That's the one going up the stem here. And when there's enough ionized gas between those two capacitors, there's a spark gap. The electricity jumps to the second coil, and all of those electrons go thousands of times per second up to this toroid on the top. And eventually there's enough electrons up here to break out as ionized gas around the toroid attracts those electrons from a negative to a positive charge. And this is when you see those big arcs of plasma coming off the top of a toroid. We're not going to turn this big one on tonight because there's so many electronic devices up here, it would melt them, it would short them out. And so I brought some smaller versions of this Tesla coil that are safe for the stage, that won't damage any of our AV equipment. And the first one that I want to share with you is very small, but it kind of illustrates Tesla's idea. And we're going to use different ampules to illustrate what this looks like on a smaller scale that's safe. Okay, so in this first one, I have that primary coil. It's just a small wire wrapped around the base. And again, there's a spark gap inside of this that leads to the secondary coil. And I've got just a small LED in my hand. Now, his dream was that you can get a light anywhere near that toroid, and the electrons that are around the toroid become ionized, and that transfers wirelessly those electrons to the electronic device, turning it on. And so I was thinking, how can we do this on a scale where you can see different colors of light? How can we bring in our knowledge of different noble gases with this experiment? And so we thought one of the things that we could do is bring our high frequency generator. Now this machine is kind of like a Tesla coil. It has a primary coil at the bottom of it. It has a small secondary coil that goes right up the stem. And at the end of this spike, what you'll see is a little bit of plasma coming off. But it's not so much that it would short out devices on our stage. So we feel like this is a little bit safer for our uses tonight. And what's interesting about this particular device is that you can hold it up to different sources and you can actually see the plasma coming out.
Mr. Montgomery, bring the lights down, please.
So hopefully from where you are, you can see some of that plasma going out to the ampule. And this ampule is filled with a noble gas that's called neon. Let's forward to our next slide on noble gases. And I want to talk to you a little bit about why it's red. People ask, why is some gas red? Why is some gas blue or silver? And it all has to do with the photons and their frequency. Whenever you have enough energy traveling through an atom, its electrons get excited. And they're forced to outer energy levels. And I always teach kids, this is like climbing a ladder. When I climb a ladder, I transfer my energy through body heat and sweat. When electrons climb a ladder, they transfer their energy through something called photons. And every photon has a different frequency, it has a different wavelength. When you see the color red, you're seeing a wavelength of 700 nanometers. When you see the color blue, you're seeing a wavelength of about 432 nanometers. And of course, I have students to say, well, what causes those wavelengths to be different?
Tell you what, let me hold the Tesla coil. I remember last year I got hurt, so let me hold it.
This makes me nervous. I think Mr. Crosslin has a plan here.
Thank you. Energy off.
I am holding argon. Argon has a frequency of about 432 nanometers. It should create the color blue, kind of silvery.
Do I touch your hand?
I hope not.
Lights out.
Oh! Whoa! You do want payback. That's a good shot.
That was a good one.
So if you hold this up, you can see that argon definitely has a different frequency. Kind of blue, kind of purplish. And that's about 432 nanometers. Sometimes people say, well, Mr. Ramsey, What's a nanometer? A nanometer is 1/billionth of a meter. That's 10 to the power of -9. Now you don't have to measure it in nanometers from press to press. You can also, this is xenon that you're seeing, kind of a silver gray light. You can also measure wavelengths in hertz. Those are vibrations per second. Xenon has about 200 trillion vibrations per second. That's what you're seeing here. As those electrons get excited, they wear out, they return to their original energy level, and they transfer that energy in the form of a photon. Remember, a photon is a particle or a wavelength of light. That's what you're seeing.
Can we do 2 of them?
Let's try it out. So I've got argon here and xenon. We're going to try to split the plasma between them at the same time.
Let's turn the lights down all the way and see what happens. We turn the lights down in the house. Here we go. That's pretty cool.
Rick is getting that awfully close to me, people.
All right, turn the lights down. Okay, I think you've introduced a little bit about colors. We're going to try something now, which is one of my favorites. It's called the ooh-ah flame test. So we'll need some methyl alcohol. Keith, it's in the back there. We have here, I need my help. You guys ready? You got your goggles? Got our goggles? Okay, put your goggles on. We have 5 different chemicals. And this is one way that scientists try to identify different types of elements by how well they burn. So we have lithium chloride, we have potassium, we have strontium, we have copper, and we have salt, regular table salt. Mary, can you tell us anything about any of these?
Yes, what would you like to know about? I can tell you all about copper. Copper, did you know it's only one of 2 metals that is not silver? Justin, did you know that? And you know what's really cool about copper? It actually has an antibacterial quality to it. So they put it on doorknobs so that when you touch it, bacteria can't grow. Pretty amazing. What do you know about lithium or any other of these, Justin?
Well, lithium, I know is a common battery, lithium battery. And I know another common one is meditation.
No, not on lithium yet, thank you, Justin. So we're putting a little bit of alcohol here. This is a special fuel that will cause these things to burn. And copper, you probably heard of copper. Wonder what color copper is going to be. Any ideas?
You know the Statue of Liberty is made out of 150,000 pounds of copper. And you know, it looks green to me.
Okay, we got these nice and mixed up. Are you ready?
Yep.
All right, let's put the flammable material off the table. Mr. Ramsey, you want to take this, please? There we go. Okay. And let's
Hey,
find...
Mr. Crosslin, did you know that potassium is found in chocolate?
No, I did not know that potassium was found in
That's my
chocolate.
reason for eating it. It's so wonderful.
Okay. Miss Mason, do you know where my lighter is?
No, but I have mine.
Let me borrow your lighter. Thank you. All right, so let's turn the lights down. Let's do the first one. Here we go. Ready? Let's see what this one is. This one's going to go. This is regular salt. Now you see that it's burning blue from the methyl alcohol. That one's a little ooh. Let's have a little ooh. Here comes our next one. Let's see what this one's like. Ready? Ah, there we go. You guys want to line those up? Now, let's see. This might be a real big ooh. Let's find out. That's better, yeah. And you start to understand this is how fireworks make their different colors. Let's see what we got here. We got. That's pretty cool. Ah, so we have ooh, we have ah, and we have one more. That's pretty cool. The ooh ah flame test. Very good. That's really cool. Now, that fires need three things. They need fuel, they need oxygen, and they need temperature. So to put these out, we're going to take away one of those, which is oxygen. So just cover it up. Cover it up. Now, what I really love about this is scientists can look at the stars, and by looking at the stars and seeing what colors they are, they can tell what elements might be in those stars or in those planets. In fact, on our next slide, I get to say this kind of fancy, famous guy. This is the birth year, the birthday for, do we miss Mendeleev? Let's go back to Mendeleev. There was a Russian chemist by the name of, here he is, right here. And this is his anniversary, 150 years. You guys have received a periodic table of the elements, 118 elements. These are the things that nature uses to build all molecules. Repeat after me. Here's his name. Ready? Dmitri. Ivanovich. Mendeleev. Let's do it together. Dmitri Ivanovich Mendeleev. Come to find out, this is nothing more than a cheat sheet, so he knew which elements were what. But you have that periodic table of elements, and Mr. Ramsey, I think you're up next. Let's go to green fire tornadoes.
So just like in the Luau flame test, where you saw different chemicals emit different photons of light from the light spectrum, we want to do a special demonstration with a fire tornado. But it's not just any fire tornado. You're going to see green fire, and we're going to use methanol. That's right, pour it in there. And go ahead and pour that in. We're going to use methanol and boric acid. And when boric acid combusts, it gives off this brilliant green light. And we're going to turn around a little bit. Just turn yours a few times and stir it, just by turning it. Now, when we ignite this and it begins to combust, one of the interesting things about fire tornadoes is why the flames start to spin. And Mr. Crosslin just told you that fire needs oxygen. But when you have oxygen entering a fire source through perforated angles, you have the centripetal force of that air entering this wastebasket from different angles as it turns, and that influences how the fire combusts that oxygen. If the oxygen is turning, then the fire will follow the oxygen, the source of its fuel, in the same direction. And so if you can look closely, when we ignite this, you'll see the actual vortex of the flame follow the direction that we spin the basket. It's really rather amazing. So if our partners are ready, okay, and go ahead and ignite. And you'll see that green fire. And as you spin it from the bottom, you'll start to see a vortex climb out of the basket. You gotta get going a little faster. Spin it from the bottom.
This is where you clap and go ooh and ah. Pretty cool.
That's our green fire tornado. And now for safety, the way that we're going to put this fire out is a tool that many of you have in your own homes. I think you'll recognize it. We plunge it. Now, Mr. Crosslin told you about Mendeleev and the periodic table, and we want to talk about a lot of chemicals tonight. And the next demonstration we want to do is a decomposition reaction using potassium chlorate, sugar, and sulfuric acid. Now, the way this demonstration works is when you add a catalyst, some chemicals will speed up their rate of reaction. And so the catalyst that we're going to add potassium chlorate, sugar, is sulfuric acid. It's going to dehydrate the sugar. That's the fuel source. The sugar is going to produce the heat to break down potassium chlorate into potassium chloride. It's going to release an amazing amount of energy, 2,023 kJ of energy per mole of sugar reacting. And so here we've got a crucible with our potassium chlorate and sugar And I'm just going to add a drop of sulfuric acid. And we've got a flame retardant bug underneath it. You're going to see a lot of fire all at once. It's going to be a white fire. And it's probably going to smell like something that you're used to when you go camping. How many of you have smelled burnt marshmallows when you've gone camping? Well, what you're really smelling is decomposed. You're really smelling decomposed sucrose, burnt sugar. And you'll probably smell that tonight. So this is a very exothermic reaction. You're going from chemical potential to chemical kinetic energy very quickly in 3,
Use
2,
your glasses. Use your glasses.
1. Here we go.
This next one, there should be some loud noises. As Keith is getting ready, we have several gases we're going to explode. My favorite gas, while he's getting ready, is this one right here. This is helium. Helium, you probably have gone to the store to buy a helium balloon. And I'll tell you about helium, was discovered on the sun first. Scientists actually had seen helium on the sun and never found it on Earth. But something bad happened several years back. Let's look at the next slide here. Germany was making large dirigibles. Dirigibles were these giant ships that had iron inside of them, and they were filled with hydrogen. And this is the Hindenburg that made its voyage across the Atlantic and was getting ready to dock at Newhurst, I think,
Yes.
in New York and in New Jersey, and it actually, static electricity from that metal tower sparked this, and it was a terrible tragedy. So they wanted to use helium. But our government said, no, we should probably keep the helium for ourselves. And this is probably one of the last of the dirigibles that used hydrogen. We found helium quite by mistake in Texas. They found this helium coming up out of the ground. They kept it secret for 30 years. There was a special kind of rock under the ground. The helium had come up and was trapped under this rock. And when they found that rock, they kept it top secret. The first thing they did was they took the helium and put it in these big containers. They came back in a week and it was gone. Helium is an escape artist. It goes through everything. In fact, you can go down and buy some at Party City, but it's harder to find. If you saw any of the movies of Terminator, you saw that liquid stuff, liquid helium actually will crawl straight up a wall. So why is helium important? Helium was important because when we started going into space, they needed something to test the engines. If they filled the engines with gas and lit them on fire, as we explored the heavens on columns of flames, the engines would blow up. So they'd fill the engines with helium and test them for leaks. And when we sent man into space and women into space, they put on spacesuits, they filled it with helium to see if any helium would go out. Well, in 1977, the government said, we're done with helium, we should let the private industry do helium. So they ordered the guy in charge of helium to sell it all. When they sold all the helium, the companies trying to make helium could not sell helium because it was so cheap. We ran out of helium almost. So now helium is really hard to find and to buy. Party City wants to buy it, but it's saved for medicine, it's saved for science. Even the Indianapolis 500, when we release all those balloons, has a hard time feeling helium. Are you about ready up here? I got to say one more thing. Ready? If I do this right, let's see here.
Helium is my favorite element tonight. Thank you very much.
So Mr. Crosslin told you a little bit about the Hindenburg. This was a disaster in 1937 as German scientists wanted to use hydrogen to fill their Zeppelins, their giant blimps that look like our Goodyear blimps today that are filled with helium, which is much safer. But they didn't realize that just a static shock would ignite all the hydrogen gas in that Zeppelin and cause over 30 people to pass away. And so we want to reenact the Hindenburg tonight. We've got our volunteers here with us. And what we're going to use is a balloon. This is going to be our Hindenburg. And what we're going to do is we're going to decompose, well, this is a single displacement reaction with hydrochloric acid. And I'm going to use as my catalyst tonight aluminum foil. And when I put the aluminum foil into the hydrochloric acid, what's really happening is I'm reducing hydrochloric acid, and it's going to create aluminum salt inside, and it's also going to freeze, it's going to displace pure hydrogen gas. This is a very exothermic reaction, so in about 30 seconds, you're going to start seeing fizz inside here. The outside of this is going to get very warm, and you're going to see water droplets, condensation coming up here. And this balloon is going to start to inflate, but it's not going to inflate with helium, it's going to inflate with pure hydrogen gas.
What does exothermic mean, Keith?
That means it's going to release a lot of heat. So endothermic is when you absorb heat, like when a firefly produces bioluminescence, it actually lowers its body temperature. But exothermic reactions give off heat, they create a higher temperature. And so usually what happens when we put in our tin foil here is galvanized, and the acid starts to decompose that, and it starts to feed on that aluminum. You can start seeing bubbles there. You see that? Look at our balloon. What's happening to our balloon up here? It's going to start to change. Now start feeling the outside of this. Is it starting to feel warmer to you? It's going to get really hot. Watch the balloon.
You can see these experiments. Keith does this with his 6th grade class. If you visit Ramsey Land on YouTube,
feel that? It's getting too hot to touch now? It's getting really hot now, isn't it? Pretty soon I'll only be able to hold it from the top. I won't be able to hold it from the bottom. This is just too warm. Now you can guess what we want to do. We want to get a flame really close to this balloon and see if hydrogen gas is really flammable. And so we're going to let that balloon inflate a little bit. I'm losing a little gas around the edge here. You need to stretch out this balloon a little. You want to feel it again? It's getting really hot.
That's enough?
Yeah.
Okay.
Okay, so we're going to twist off this balloon, and we're going to light one of our candy canes. Go ahead and light that up.
Okay, we got these two up here too.
Okay.
Let's have one of one of our volunteers. Which one do you want to pick? The red, Jack, the red or the green balloon here? The red, okay, come over here. The red balloon is regular air. Hold that underneath it, and let's see what happens. Ready? Slowly, still lit. Nice pop, no flame. Let's see what's happening. Let's try this one over here. Come over. This one is helium. You got the fireball. This is the helium. You know where helium comes from? I hope all for Christmas all she wants is a fireball. Get a bit closer. Here we go. Ready? Yeah, ready? And this one is helium. No fireball. How are we going to get fireball?
Here's the next one. Small balloon. Be a little safer here.
Here's
But
this
we
one.
should see some fire. Yes. All right.
Should we let her do it? Should we let her do it? All right, here we go. Come around this way.
Come on up.
Keith, you want to do this one?
She's got it. She's got it.
All right. You've done it before. All right. Here we go. 3, 2, 1.
That's a strong balloon.
Could be a death. Maybe Keith, maybe you tell us the wrong thing, Keith.
Whoa! you kind of had a spurt of fire.
Yeah, a little bit of Yeah, and we have a fire blanket for this.
We have a fire blanket for that.
And let's give him a round of applause. Thank you. Too bad the Hindenburg didn't do that. That would have been better if the Hindenburg would have done that. Keith, this next one I'm a little worried about.
Yeah, we should be worried. This is just another example where Rick wants to light me on fire. And I can't blame him, honestly, people. And so what we have here is a special gas that we've created, and we've trapped it in our beach ball here. We call this beach bubbles. And we're going to have this gas go into a bubble mixture. But we're not going to blow the bubbles, we're going to ignite the bubbles while we're holding them. And we're going to pass the bubbles one to another. It's like passing the torch.
Let's just try you first, Keith.
Well, yeah, we knew this would happen, right?
Let's just see what's going to happen. So,
All right, I'm going to roll up my sleeves here. Because I have, a couple arm hairs left, not very many, but there's a couple there. And I'm going to get my hands wet. And Rick is producing a lot of bubbles with our special mixture. Perfect.
you think air is in these bubbles, Keith?
I hope it's just air. That's good.
Okay.
Okay.
I'll let you go first.
All right, so that's what
I got my lighter.
All right, so what Rick is going to do, hopefully, is just ignite the bubbles and not Mr. Ramsey, but you never know. All right, ready?
The lights out, please. Let's see. I've been waiting a long time for this.
In 3, 2, 1. There we go. Very safe, very quick. Only the bubbles burn, not Mr. Ramsey.
Try it again.
Rick's plan was spoiled.
There we go. Try it again, Keith.
Yep. All right, let's put some more.
You guys want to get your hands filled?
All right, here we go.
Make sure your hands are wet. You want to get in line? We'll pass it on down. You notice I'm not doing this? get your bubbles. Here we go. Ready? Barry, you need bubbles.
Four bubbles.
Now, here we go. One last try, Mary. Okay. Let's give him a round of applause. Good day. Okay, what's our next week? I tell you, we're going to end this section with, I need my volunteer. Here's my standing wave volunteer. Here's my standing wave volunteer. You have the papers, this standing wave? Who are you? Where are you? Elves, where's my standing wave? I think it was, here we go. Come on up. Yep, hurry up, hurry up. Here we go. Just come on up. All right, we'll do it the old-fashioned way. I need you. Get up here. Let's give a round of applause. Thank you. Let's give her. Hurry on up. Come on. We're going to do, if you can get a gas to vibrate, you can make some sound. What's your name? And what school do you go to? Chapelwood. You're in Miss Mason's class, right? Hold that tight. So what we're going to try to do here is show you that sound is vibration. If you can get air to vibrate, you can make a sound. So hold it tight. And this is a low wave. Low wave. Just hold it with two hands. Let's see. Let me see if I can make a little bit of a better wave. And maybe if I can do it really quick. You can see 3 or 4 waves. You can see the nodes, you can see the trough, the crest. But let's do some sound vibration. Ready? Hold it, and I'm going to send some sound. Maybe you guys can see this. Watch. You see it traveling through there? On the count of 3, you hit it. 1, 2, 3. Let me try it. 1, 2, 3. Hey, what's going to happen if we both hit it at the same time, do you think? What do you think? Let's find out. Ready? On the same time, we hit it really hard from the top. 1, 2, 3. See how that kind of went back and forth? So that's a little bit of introduction. Where's my, let's give her a round of applause. Thanks for coming. Where's my son? Back to my table. Where's my sound sheet? The sound, no, that was right here. Here we go. So we're going to try to show you with a torch if we can make, maybe we can make sound just by a gas. So we can start this up. This is a butane gas, and I have a little bit of a pipe right here. My pipe is empty. It's got a little screen in the middle of it. And if I can heat this up, you might be able to hear it. Listen, listen. If I hold it just like this, did you hear that? So what I'm doing right now is I'm heating the bottom of this, I hope. And as I heat it up, can you see it red in there? So the air should start vibrating up through convection currents, and we might get some sound. Let's hear, listen. If I turn it like this, no. When I turn it like this, it can't vibrate nice. When I put it straight up, it vibrates right up the top of the tube. And it might even do something really kind of fun like this. Ready? Gotta get it hotter. When you get it hot the first time, the air is not as cool compared to it. There we go, ready? There it goes. Hey, thanks a lot. Thank you. That's a little bit of gas. Last year we tried this and it did not work. So, a good part about being a scientist is not giving up. So let's bring this out, Pete. And got that? This is the Rubin tube, 0.20. So, the Rubin tube is kind of cool. Heinrich Rubin, in 1905, a German physicist, thought, oh, it's nice to see a standing wave, but what if we could see it with fire? And so here's what I'm going to try. You got that turned on a little bit? Let's see if we can get this ignited. So I have a tube here that we made. Anybody bring those marshmallows? A little bit lower heat, there we go. And so you can see us straight away, but if I talk to it like, Merry Christmas! Did you see any changes? How about, ho, ho, ho! So I have a balloon on this end, but I thought, you know, I'm a dad and I got dad music. So let's see if we can try this here. Let's see if I got. This is hooked up to a Hertz generator. I can go. All your dogs at home are going, huh? What? Dogs can hear really well. High, low. I'll try the volume. My daughter's going, Dad, stop. Stop. There we go. All right, so let's get it a little bit lower. What do you think is going to happen when I put this here? Let's find out. Let's see what happens. Turn it down. Turn the sound up. Low sounds seem to do what, Keith?
Higher wave. Low sounds make a longer wave, high sounds make a shorter wave from crest to crest. So if You want a big wave, you need a low frequency, high amplitude.
Let's see if we can get some music going here. Let's see. One of my favorite songs. Let's see. How about Unforgettable by Nat King Cole? Sounds good? Sounds good to me.
Yeah.
Here we go. Hope no one calls
Lots of
me.
low notes and unforgettable.
Hope nobody calls me during this. We'll see what happens. Sorry. That's good, I got it. Mr. Montgomery from the booth just called me. Thank you. Go ahead, go. I'll put you on there. We'll see. Here we go. This is song number 1. Anybody wants to dance in the aisle, it's okay. I will install these in your backyard for a small fee. So thank you very much for the Reuben tube, and thanks for having me here to keep that in the aisle. Okay, we're going to transition to something even more interesting, and that's our motion. We'll get that out here. So this is our last segment. How are we doing on time? Only 3 more hours to go. That's good. This is our motion one right here. Okay, here we go. Going to go to the next slide, Mary. We got this. Keith. Okay, so motion. Really quickly, there was a guy named Aristotle. You've probably seen him. He had long hair. He was born 300 BC, and he thought motion was something that was natural. He thought there was 2 types of motion: heavy things like like water and earth move down. Light things like fire and air moved up. But we're here to know today to know a little bit more. Mary, next slide, please. The motion we're going to talk about today, though, is by a guy by the name of Isaac Newton and his laws. This is kind of fun. We did this last year. I hate this part. No, I kind of like this part. We're going to use a gas to make a motion. Keith and the gas we're going to use is something you breathe out every day: carbon dioxide. And our friend Isaac Newton said for every action there's an equal and opposite reaction. Let's see if this works. So I'm going to sit on this, I hope. Not sit on my radio. Mr. Montgomery, don't call me. Are you guys ready?
I've heard about that thing.
Mary, are you ready?
I'm ready.
Here we go. Cover your ears. This is kind of loud. For every action there's an opposite and equal reaction. Cover your ears. That's pretty cool. That's a lot of motion, a lot of gas. But let's take we bring that lights. I had a chance to go to England, and let's check this out. Short video. So this is at the famous Wolfram Manor, where the famous apple tree that Isaac Newton on his house there. Is it still playing? Okay. And the tree is over 400 years old. It died. They propped it back up. And when I went there, I thought, I have to try this out.
After tea, went for a walk and observed an apple falling.
It's not every day a science teacher gets to reenact the famous experiment and demonstration of Isaac Newton, but here we go. The Kent apple tree on Isaac Newton's birthplace, and an apple from that tree. Same result.
And he thought, why does the apple always seem to fall towards the earth? Why doesn't it fall perpendicular? Or, for that matter, rise up? But it always falls down. Perhaps there is a force that pulls it down. And of course, by now you know that the person we're talking about is Isaac Newton.
That was Isaac Newton, right? And the force is gravity. So we're going to try some things. My friend John, would you come on up? John is our math teacher in the district. I love science. This is John Albright. Everybody give him a round of applause here. So we're going to do some tests, John, with how things move. And for example, the first one's over here. Just would you move that table out of the way? So we got I got a wheel right here. This wheel would go down if I released it because gravity is a constant. Gravity is here on Earth. It's a constant. It's on the moon. It's in space. And if I can get this thing going with my wheel here, I'm giving it more energy, I'm speeding it up as fast as I can get it going. And this should be kind of cool if I can turn it like this. It should stay up and not fall over because it has something called angular momentum. In fact, this is the same thing of a bicycle. If you see a bicycle, as long as the wheel is spinning, the person doesn't fall. Preschool teachers. As long as the bicycle wheel is spinning, it resists pulling off because it's called something called moment of inertia. John, you're like a big guy. Maybe you can help me with this here. All right, John, we got, you're a math guy, right? Same size, same shape. What do you call that? Congruent. Okay. So we'll have a little contest, John. These are the same mass, same length. Which one do you want? Okay, you take that was a good choice. So they're the same mass, the same weight. So let's have a contest, John. Come next to me. Hold it like this, and we're going to spin it 10 times, okay, without breaking it. We'll see who wins. Ready? Set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What are you on, John? When you do it, you can try this at home, even with a pencil. Put a weight close to the center of gravity. It has little inertia. Put it farther out, it's harder to go. Of course, John, if I got you, keep doing that, John. If I got you going like that, and I moved the apples in, it would be easier. Let's try that, right? Let's try that. Here, John, do you get seasick much? Okay, well, let's have her take this for me, Keith. This will be better if we can reduce friction. So this is from the Ben Davis Physics Department. And John, I want you to sit on this. Standing would not be good. And try to get in the middle of this. And put your feet up on it. And the most important thing about this is not to hurt me. Okay? And unless your wife wants some rug burn on your face, keep your arms out. So I'll get this spinning. And the more I get it spinning, this is the same thing that airplanes use. Now, John, it's pretty easy to go up and down, right? And it's pretty easy to go sideways along the axis. But try to twist a little bit and see what happens. See how he turns? Twist it the other way, John. The angular momentum resists change. Now, let's put it back up straight. Can you imagine, boys and girls, if we had this straight, and airplanes use this. They have one like this, they have another one like this, and another one like that in a box. And as long as they're spinning, the pilot can know if the plane is going this way or that way, even in the dark. This is called inertial guidance that airplanes use all the time with 3 gyroscopes. That's kind of cool. Let's give them a round of applause. You're doing good. And this is called precession as it goes around. It always, depending on the spin and how you hold it, it goes around different way. Now, John, this next part is kind of difficult. Have you ever heard of Peggy Fleming? Oh, you're too young. Anybody? Peggy Fleming? So she was an ice skater. So let's put your arms out. Now we've changed his mass is the same, but his center of gravity's changed a bit. So if we spin him around, you got some long arms. Let me know when you start to get sick. We have a bucket. Now, what was going to happen when we change his center of gravity? Watch. Make a fist, John, and bring your arms into your chest. Bend over a little bit. See how he's going faster and arms out? Okay. It's better if you don't look at anybody. Let's try it with some added weight. You okay? How many fingers are on now? All right. Jack did a lot better than you have to say. Okay, so let's try it. Let's get him going there. And he's going kind of slow. 1, 2, 3, change your, and he spins more. And open, slow down, and spins one. Let's do one of our elves. Let's have that the one elf right there. Come here. No, right there. What's that? Yes, the white sweater. John, I'm going to switch you out. Are you okay? You sit right here. Justin, help me on this. Have a seat here. Now, switching it up, John, I don't want to be rude, but he's got a lot of mass. You have less mass, okay? That's a compliment. Say thank you. And so, with less mass, this should be a bigger difference, and we should spin you faster. All right, so put your arms out. Let's change your mass and your hold them out. We'll get you going. Throw up on me. Let's go a little bit faster. There we go. Don't hit me. On the count of 3, bring them in. 1, 2, 3, and bend down. And one more time. And out. Now, boys and girls, you can try this at home in your mom or dad's office chair. Oh, you stop it. Let's give her a round of applause. Thank you. I'll tell you, where's our table? Here's our table. Now, thanks, John. The bathroom is out to the left. So, when I was a kid, we watched the Ed Sullivan Show, and there was this guy that would spin plates. He would spin plates. So I think with science, maybe I can do this. So I've been practicing maybe for 5 minutes. I hate this part. Here it comes with gyroscopic stability. And I get it going. And I get it going. And well, as long as it's spinning, even if I tip it this way or that way, Mary, show yourself, Mary. Whoa! Chapelwood. Whoa, Maplewood. But you know, we're not professionals. We have some professionals in the house. Come on up, ladies. I'd like to introduce the Ben Davis girls varsity basketball team. Come on up. Let's see these stuff from there. Let's see if you can keep it going better than these guys are replaced. There we go. Keep it spinning. Go ahead. They said you could spin this, but you better get some spin.
Hey, may I?
Go ahead. Yeah.
May I?
Yeah. Here we go, Mary. Justin, you're in charge of keeping these going. So we also have some other spinners in the house. Where is our friend Ben? Where's Ben at? Ben, come on up. Ben, this is Lisa's son. He's on his way to college. This is his last chance to be in a science show. Ben, show us. He's another professional. Keep those basketballs going, ladies. This is going to take like 20 minutes, 30 minutes. Ben has what's called the Diablo. And the Diablo is a pretty cool spinning thing that we completely messed up for him. While he's getting that ready, this is my only trick. I'm selling these part of the Wayne Township Education fundraiser. These are Isaac Newton earrings. And an object stays in place unless the force acts upon it. Anyway, how are we doing here? Oh, good. Look at Ben. He's spinning. Now, all the things you see spinning are balanced. Good job. Move up a little bit, Ben, from the front here. Because what if you try to spin something that's unbalanced? What we happen to have here is some professional unbalanced spinners. Can we have the Ben Davis ROTC and our also spinners come on up? Guys, come on up. Let's give them a round of applause. Keep those balls going. Let's have here's this Cameron. Cameron, come over here. You guys, the gentleman on the other side over there. So Cameron, keep it spinning. This is not balanced. How do you keep it spinning? Gravity. Okay. All right, let's start spinning and see. Now you can notice she has to hold hers on the edge. And our gentleman down there, let's see your spins going on. And they keep that going and spinning. Now that's really cool. Let's give a round of applause here. We have planes, balance spinning, balance spinning. We have a sword, and you notice where she's holding that it's also not in the center. And I'll tell you, this is pretty exciting, guys. You want to show us one more thing of the routine? Let's go through it. Keep spinning, okay, we're good. And I'll tell you, you think this is the finale, but it's not. Let's bring down the lights. Can we have the spinners lead the stage? Because we have a treat for you. Everybody, let's give them a round of applause. And ladies and gentlemen, can we turn the lights off, please? Next slide. Boys and girls of all ages, we have a very special treat straight from the Wayne Township Preschool. We have a teacher par excellence, Allison Kippers, and the baton science of spinning. Spotlight, please. Let's give her a round of applause. Thank you very much. Right on time, it's now time for the grand finale. They're going to get these set up. We have presenting Elephant Toothpaste. Followed by Smoke Green Vortex. We have asked 3 people to do the Elephant Toothpaste. Would you come on up if you've been selected? 3 people, please. Here comes our, ready, okay? What we got? Let's hear it one more time. Congratulations to Allison for a great job. Allison. Now we got the smoke machine plugged in. Yes, okay. Where's our 3 volunteers? We got them? 1, 2. Where's our 3rd? Our goggles? We got one up. Elf's giving me one more volunteer. JC down here. Okay, you got her? Okay. You're right here in the middle, young man. Keith, you got these ready? Okay, we got the Elephant Toothpaste coming. This is an exothermic reaction. You got it in there? All right, let's go ahead and put the soap in. Keep the soap, he's coming, you got the soap.
So this is a decomposition reaction using hydrogen peroxide, whose chemical formula is H2O2, kind of like water, H2O. but it's got an extra oxygen atom, and we're going to free that oxygen with a catalyst called potassium iodide. And when we add the catalyst, all that oxygen, hopefully, is going to be trapped inside the bubbles. And you can imagine what's going to happen when those bubbles rise inside of your container. So in one container here, we're going to add one color of food coloring. In another here, we've got blue food coloring. And we want to see if we can get red and green. So we're going to add a little red over here. And just wash that around a little bit. And we're going to add green over here. And this is an exothermic reaction, so when you see the bubbles rise, you should also see a little bit of steam coming out. You should see a little bit of heat coming off the top of it as well. And so in this beaker here, we have homogenized potassium iodide. This is the catalyst that's going to increase the rate of the reaction. So if you just leave hydrogen peroxide out in the open, it will react on its own. It'll release oxygen on its own. But if you add that catalyst, it increases the rate and it's much faster. So
we set up?
We're all set up. We're going to go from chemical potential to chemical kinetic as soon as they add their catalyst. You ready? So pick this up. You're going to pour all
I got the toothbrush for the toothpaste. We'll do one at a time?
Sure. Roll it. Watch the bubbles. Watch the bubbles. There it goes. Whoa!
Very quick. You ready? Here we go. Pour it in.
Feel
Bring it
really
in.
warm. Very exothermic.
Okay.
Watch the bubbles. Here they come.
More heat.
Okay, we have another. You ready? Here they come. Put your hand over it. You can feel heat coming out. You feel steam coming off of it. Still reacting. Still reacting. Do that. Feel that?
That was still going. What did she do that we didn't do? Still going. You guys get your, let's give them a round of volunteers, round of applause right there. I hope so. So our next one is our giant smoke rings, and we get our smoke machine going. These are vortices that you see. You're going to see these. Let's see, we got. Here we go. And hopefully we get this going. You guys got your smoke. See if you can hit somebody out in the audience with that. No, it's sputtering. There we go. It's going to take a second for that to go. Let's let that one continue. Here we go. Green light to come on. Here we go. There we go. And this is, we have spent a lot of time talking to Ben Davis about the fire alarm in the basketball game going on. Here we go. And hopefully we got some here. Here we go. And here we go. Let's start this finale off with just Mark, you're going to bring the house lights up a little bit. Let's see what's going on here. One more shot. So Daniel Bernoulli said, if you can increase the flow of a liquid or a gas, next slide, you can actually decrease the pressure. And if that's the case, let's see what happens here. You guys ready? Please stay in your seats and we'll try it out. Don't get any ideas about toilet paper in anybody's house. But if you know the science, I guess it's okay. We have 2 more to do. One of my favorites is the whoosh bottle. And the whoosh bottle, we put some special fuel in here. And the fuel was a liquid. We're going to take the lid off. We'll need, Allison, would you get us the candy cane, one of the good candy cane candles? And we put some fuel in here, and we don't want the liquid, we want the vapors. It's a special fuel, and we'll try, I have a blast furnace here, blast shield here. Oh, I got my special sword, we'll be okay. Do we have volunteers for the whoosh bottle? Did we have volunteers for the whoosh bottle? No, I don't think we did, we just all right, let's turn the lights out. And you should hear whoosh, and we turn all the lights off. So now we should be able to see a really cool blue flame. Let's see what happens. Ready? Maybe? We'll see. That was cool. You have to try yours, Justin. All right, let me get the shield. Where you at? Okay. Here we go. Whoosh bottle number 2. Did you shake it up? Yeah. Here we go. Better just use this. Get down low. And run. I mean, a little jump back. All right, you ready? Get the shield. Get the shield, Justin. Allison, you want to do this one? All right. A preschool teacher that plays with fire should be okay with this one. There we go. Go slow, go slow. That is always better. I mean, you have no one do that. Move that away, please. Thank you. All right, here we go. Let's turn the lights on. A byproduct of combustion is water. That's water. Next time you see a jet airplane going across the sky, that white stuff you're coming out is because it's burning jet fuel, combusting, and sending water vapors out, which is pretty cool. All right, we have some liquid nitrogen. Our last one. We got liquid nitrogen, guys? It's on the table here. You guys want to do it too? Mary, you ready over there? Mary, over there by the projector. Okay, I need more liquid nitrogen. Bring me the whole thing of liquid nitrogen. This next one I'm going to do with liquid nitrogen is pretty cool. Bring me the whole dewar of liquid nitrogen. We have a lot of liquid nitrogen. In fact, what's going to happen, you want to fill another one for me? If we put this in here, that's pretty cool. We're getting bubbles. In fact, lots of bubbles. Dump some more water in there. Here we go, we have water here. Go ahead and dump yours in over there. This reminds me of something. This reminds me of that song. What's that? Let It Go. What is it? Frozen? What's that? That reminded me of Frozen. Nope. Oh, there we go. Wait a minute, I think it's the wrong slide. You guys know this song? This is supposed to be a science show.
Snow glows white on the mountain tonight, not a footprint to be seen. A kingdom of isolation, and it looks
If you
like
guys know it, sing it. Stand up.
the wind is howling.
Bring the lights up.
The swirling storm inside. Can't hear heaven knows I will try. Don't let them in, don't let them see. Be the good girl you always have to be. Conceal, don't feel, don't let them know. Well, now let go, let it go, let it go. Can't hold it back anymore. Let it go, let it go. Turn away and slam the door. I don't care what they're going to say. Let the storm rage on. The cold never bothered me anyway.
This is as good as my dance can get. Come on.
Distance makes everything seem small. The fears that once controlled me can't get to me at all. It's time to see what I can do to test the limits. No moves for me. I'm free. Let it go. Let it go. Let it go. Let it go. You'll never see me cry. Here I stand, and here I stay. Let the storm rage on.
There's the building.
Power flurries through the air into the ground. My soul is spiraling in frozen fractals all around. And when thought crystallizes like an icy blast, I'm never going back. The past is in the cold never bothered me anyway.
Let's give her a applause. That baby's still sleeping. So the cold never bothered me anyway. This cold would bother you. 327 degrees below zero. We have some liquid nitrogen in the Grand Valley. I want to thank everybody for coming. We worked really hard on this. So give everybody, these people a round of applause. Remember, you want to be on the good list, not the naughty list. So Santa will be here afterwards. Here's what we're going to try to do. We have 1,000 ping pong balls. We have some gloves. We're going to put some liquid nitrogen in a bottle. We're going to put the lid on the bottle. That liquid nitrogen is going to try to expand. It will expand really quickly. And it will expand so quickly that if I keep the lid on, it will explode. If I drop it down, and Mr. Ramsey drops in 900 ping pong balls, Everybody close your ears, and we should have quite a grand finale. Let's see what happens. Here we go. Sandra, are you going to help on this here? Here we go. So right now it's liquid nitrogen at 327 degrees below zero. I hate this part. Here we go. Cover that baby's ears. All right, that's pretty good right there. Right, good, Keith. So we have about that much, which will expand to about the size of a classroom. This is the part I hate. Are you guys ready? Here we go. I'm going to put it in. Close your ears. Here we go. I got to put it tight so we don't have a fizzler. Close your ears. I don't know when it's going to go. We'll find out. Thanks for coming.